have summation of these variants, but then it makes sense just to calculate one of them because they are already. So this is indeed 1 over n of the variance of one of them. On these ones, I just here work with W1, one of these. Doesn't matter. Then we can have the 1 and here. Alright, so that's sort of what it is. So, well, I mean, these are the weights, 1 over h, k x1 minus h divided by h comes out, becomes h squared. Now we have to calculate the variance of this. So, but well, this is actually not hard. So this is 1 over h squared, expected value of k x1 minus x divided by h to the power of 2. The second moment minus the first moment to the power of 2. Right? So now we can calculate. Well, this one we have calculated already. That's the expected value. It's here. Somewhere. Right? So we have it there. So we can simply plug it. So we don't have any problem with the first movement. We calculate the second. Well, I mean, the second one is also not, well, I mean, that's exactly the same way we did it the other way around. For the mean function. But then let's see what that guy is. Alright, so I'm just going to calculate the second one here. So that will be expected value k. Let's write in the square x1 minus x divided by h, which is integration on all of the real values of k squared x1 minus x divided by h times the density. Alright, then we change the variable again as we did here. Right. We have ui to be s minus x divided by that, and then we have this little transformation, so we do it there too. Right. So then will become integration on all of the r values. Then it will be k squared and u f of, so that is x1, right, becomes h times u1 plus x. The same. Alright. So that will be x plus h u1 du1. Right. Now we do again Taylor expansion. That is our Taylor expansion here. And then we plug in. So well, let's see what we really have. Remember that this is a square. Right? So here this was not a square. So that was u times k. And there you will have u times k squared in the second basic term. So that one, this term will not go off. So that will remain. Yeah? So maybe let's write the Taylor expansion here and then plug in. That will be just so we have it in front of us. X plus h u1. Taylor expansion around h0, then this becomes f of x plus u1 f prime at x. So that's the derivative times h plus, well, the other terms. So here, then I stay here. Because this term doesn't go off, then it doesn't make sense to go further. So that's the dominant term. That's the biggest term that we have. Now if I plug in here, then we will have integration over the real values, the first term. Maybe I can actually just write it right. So this will be f of x simply comes out of the integration of the first one, k squared u and dv, right? So that's one term that shows up, plus h times f prime of x integration over all of the real values. Now comes u times k squared u d plus some OH, some small term. Alright, so that's sort of what we have for the indeed variance here. Alright, well, so far so. So now if I plug this in, that expression up there, alright? And here we have h squared, then you also have this term, and then we plug them in and then do some simplification. So that's sort of what I will do now, such that this variance term, so I'm starting with this star equation, alright, here, then it becomes 1 over h squared, as we have it, times those terms. Didn't I miss some term somewhere? So then this is the first term that shows up. F of x, k squared u, integration over the real numbers, du plus, so here we have an h, one of those h's cancels, and we have 1 over h, f prime of x, integration over all of the real values, uk squared of u, du plus a little term which vanishes, right? So far so good. So these are all of the terms that we have in the first one. Now minus the second. Here we will have minus 1 over h squared times the first moment to the power of 2. The first moment to the power of 2 is this f of x to the power of f of x plus these terms. So we just plug them in. So there we have f of x plus 1/2 h squared mu 2 plus the little old term, which is more than 2. What over to the power of 2. Right. Good. So far so good. So these are basically the whole terms that we have here. So, well, this is the kernel to the power of 2. If you remember, so we assumed this to be bounded. One of the assumptions was that this is not big. And for, say, Gaussian kernel, this is indeed a bounded kernel. So that's not actually very big. Right? So that's sort of what we have here. So if you plug in these terms, do some calculations, and sort of play around with pluses and minuses, maybe I shouldn't do that, but leave it for you as an exercise, because that's not hard, it takes time, so that I cancel things. And what we will get will be that the variance of f, well, essentially, this variance we have, right, so the star equation, when you plug in here, meaning that we divide by n, then we will get the variance, because these are all of the terms, will be essentially f of x times this kernel to the power of 2 integration divided by nh. Right, so that is this nh which shows up. So maybe let me summarize. What you can do, this is very actually easy, you should do it carefully. Let's summarize things here. So this is vanishes faster than the, this is the bias. The bias equals that. Alright, so this is bias of this, so this is the expected value minus the true value. So that is the bias term. Let's look at the variance. So the variance of the estimator turns out to be 1 over NH times, just want to write it, f of x integration over r k squared of u, plus a little O term, which is O of NH. So that's sort of varies faster than this term. Let's look at these two expressions. Alright? So again, when h is a smaller value, then the bias becomes a smaller. Right? So a smaller h means a smaller value here. Right? On the other time, sort of at the same time, when h is a smaller, right? So this is in the denominator for the variance term, then the variance becomes bigger. Right? So that's the variance and bias in the trade-off that we have in the beginning. So if I make h to be bigger, then this term shrinks, becomes smaller, but then at the same time this grows, becomes larger when h is large. So this is sort of the bias and variance. Indeed, you're not happy with that.
Confused a bit between the last two lines, the one in black.
Yeah.
Yeah.
Yes.
And before that, can you explain that? Yeah. Sure. I want you to start here.
Sorry, just for me first. Sorry.
So here I have a Taylor expansion.
That's okay. I also want to ask about the last one in the black. The last in the black, yeah, the last one. Yeah, that's the second deviation, but I think it's also have the second derivative of f(x) also. Yeah, that's just for me.
Yes, you're right. Maybe that was one of the missing things. But you're right. That's the first moment. Sorry, I forgot that. And then to the power of 2. So that would be the first moment to the power of 2. You have the 1 over h, and that's the first moment. That's the second moment minus the first moment to the power. Maybe I have made more mistakes. You're fine. You can redo them. Maybe by the end of the week I will post these details also as an appendix to your assignment, but you try it on your own.
Yeah.
But I will do that carefully too, so with all of these things. So but now let's look at that one again. Alright. So that's the dominant term. And here we have also, and this the f prime, f double prime of x plus O of h squared, right? This is, so that was the term that I missed. Yeah, so now it is there too. Okay, so well now, so if I have the bias and then I have the variance, and I understand the effect of h on them, the variance bias basically trade off, then maybe I could also directly start choosing h such that the MSE is minimized. Right? But let's maybe write the MSE here. MSE of fx. Right? So that would be the bias to the power of 2. But let's maybe just focus on the dominant terms. Not on all of the terms, but only the bigger ones. But these are the small. This is the one which is the biggest part of the bias. This is the biggest part of the variance. We focus on them only. Right? That would be MSE, so we put a tilde on it, so that we remember that this is indeed the MSE of the dominant terms of the bias and the variance. So the power of 2 plus the variance. That will be 1/4 of h to the power of 4. All right. 1/4 of h4 mu 2 to the power of 2. The second derivative of x to the power of 2, so that's the bias squared, plus the variance, plus 1 over nh f of x integration over r k2 u d. So that's the MSE. MSE, the biggest part of the all right. Can you, well, I mean, sort of, let's maybe simplify it. Right? So that it looks like as a function. I want this to be a function of h and minimize it. So to find h such that this is a minimum. So if I look at that, this looks like some lambda 1 h squared plus some lambda 2 and 1 h squared to the power of 4 plus lambda 2 divided by h. Alright, so lambda 1 is this, right? And lambda 2 is 1 over n multiplied by lambda. Okay, clear? Minimize this in h. Find the minimum of that in h. Can you? Let n be there. Alright, let it be nh. That is nice. Alright, so well, let's write lambda 1 explicitly. Is equal to 1/4 mu 2 squared. The second derivative at x to the power of 2, so that's lambda 1. And lambda 2 is f of x times integration of k squared u d. Right, so these are lambda 1 and lambda 2. Now I want that you minimize this guy in h. Can you? Please. That's a function of h. Well, of course, lambda 1 and lambda 2 are a function of x, right? Well, because there is fx or in second derivative shown.
That's like, we have to 1/4 of the MSE in the square root, but you know that would be the largest.
Sorry, where again?
Yeah, the one that you allowed, 1/4, the one, yeah.
So this is.
Square.
All right, so look. MSE is equal to bias squared plus variance.
Yeah.
So now we are minimizing the MSE for 1x, for a specific x, in h.
First order condition.
Yes, please. Very good. You have to start with the first order condition. Right, so that will be the derivative of this MSE tilde of f hat x with respect to h. 1 over h.
Minus 2. Okay, so over, yeah, square. Yeah.
So just multiply both sides with h squared. It becomes 4 lambda 1 h fifth
Fifth.
minus lambda 2 divided by n. We move it to the other side, right? So multiplied by h by n squared h squared, and then took this term to the other side. And now what does this imply? For h as a function of n,
1 over 5.
very nice. So that means that h is equal to, so that's h5, this comes to the other side, becomes lambda 2 divided by 4 lambda 1,
Mm.
alright, to the power of 1/5, and n to the power of minus
Yeah.
1/5. So n was the sample size, this is some constant.
Mm.
The lambda 2 is the function of the true function, true basically PDF. Lambda 1 is also a function of the true, the PDF. And then there is also the imprint of K, the fingerprint is also here, that is, well, the second moment is the integral of K squared. They're all in here, in lambda 1, lambda 2. So it looks like that we should choose the bandwidth proportional to n to the power of minus 1. So, which is sort of some general direction of how bandwidth should be, alright, in general. Alright. Well, I mean, now, this constant that we have here indeed is a function of x. It means that for every point, then you need sort of, then this changes, alright, so then we change. So for every x that we want to estimate, then we may have a different bandwidth, many bandwidth values, right? Which is not nice. We just want to have one bandwidth, but maybe it's also nice. I don't know, right? So that's sort of what we. So maybe for each point, then it's better that we choose a certain bandwidth, right? But that's not so easy because when it comes to, so for example, remember the leaf on out, then we needed all of the observations. All of the observations, and we needed to sort of pool all of the errors in prediction together so that we could choose the bandwidth. Now, such one doesn't actually focus on this, basically type of MSE, but rather, that's possible, alright? But one may actually do the following, alright? And one defines something which is mean integrated squared of the errors. Right? So there is an MIS. You have this MSE, which we have here. Right? So this and that. So these two terms. First, take an integral over all of the support of the x. Right? Such that you partial x out. You partial it out because you need an integration. Then you will get some lambda 1 and lambda 2, which are a little bit different from those lambda 1 and lambda 2 that we have. But in the end, you will get h to be proportional to n to the power of minus 1/5. Right? So this is a general rule. Alright? And so if you see, this general rule depends on the true PDF, alright, because of lambda 1, lambda 2, and depends on the kernel that you use. Okay? So it depends on both of them, the general rule, because the constant is lambda 2, lambda 1 in this average mean integrated and squared error depends on those. Alright? So, and then there was some person some time ago, it's actually 76, I wasn't born. So what actually, the person actually said, if you have X or the data which are normally distributed, the true density is a bell-shaped distribution, and you use a Gaussian curve, right, then this constant that we have, right, will turn out to be 1.06 times sigma. One can do the calculations, and then you get this number. You should take the integrals and so on and so forth. Then you basically come up with that, right? You can check it for yourself. Right? Another sort of rule is to put, say, instead of 1.06 times sigma, then one puts 0.79 times R, where R is the interquartile range. It's 75% minus the 25% quantile, and then you put it in. So these two rules are known as rule of thumb. So this is called the Zimmermann's rule of thumb. Oftentimes, the value of the rule, so the value of this rule will be similar to the leave one out approach. They're close to each other. Right? So if you want to basically start doing something very fast without doing the rule of sort of leave one out, then you can start with n to the power of minus 1/5, and then go a little bit around, a bit more higher, a bit lower, and then you stop. So that's sort of what you have for the bandwidth choice. So that's called the optimal bandwidth choice. Right? So because optimal in the sense that it minimizes the reduce. But I mean, we also have a data-driven way of getting the bandwidth as we did it for the choice of the bandwidth. But a little bit I talked about the bandwidth, or sort of bias reduction, when I was doing the derivations. But I want not to do more theory for now, but I want to do a PDF estimation. So you go to Python, you have some data, and then you feed a PDF. Right? So that is indeed what we do is generally called kernel density estimation, KDE. Right? You may have seen it in Python, you may have used some packages which do actually these calculations for you, and these are the methods. So these are the theory behind it. But let's actually now go on and then do a little exercise together with the bandwidth choice estimation. Right? So, well, here there is on the assignment page, where is it? Not here, where was it? There. Here. So there is a data for PDF estimation. So please download that. And there is an estimated PDF. Okay, so that's sort of what we want to do together. So this is actually one of the assignments. This is question number 3, where I tell you, okay, so choose the bandwidth using the rule of thumb, which I just told you, it's also on the slide, and using the interquartile range, or you could use the variance, the standard deviation, and also we do the cross validation. So we will do both together. So, well, that's the data. You should download it, and then we can go on and then do the PDF estimation. All right. So, what is this stuff? So import numpy as NP. You may need it. Let's import pandas as PD so we can read the Excel data. Let's import matplotlib dot pyplot as PLT. Let's fix the quality. Of the plots. I think we are good to go. Let's have the data. It is there. Or I should download it. So we really review. That's my data. Let it be very difficult. Open it just to see how does it look like. I don't know. Well, these are some numbers. Just read them. Good. You have this part, yes. I suppose. Let's run it. Well, let's just remove all those. So from the previous assignment. And that's it. So the data should be here. This is the X. And that's in this column where we need essentially the data. Let's do it X row. Alright. Good. So when X is then X row. How was it? Now do we read the column? So that was 0, right? Let me see. Was not, it's not defined. What it is. So now we have the data. They are of size 1000, so there are 1000 data points. So you can read the data. I need to read it, so there you have it. And then I can continue. So what is the choice of bandwidth? Roughly. We can maybe use this. Well, sample size is 1000.
Minus 1.
So let's just start with H. Let's call it the silver man. So that will be 1.46 times NP dot the standard deviation of X times, so let's have the sample size. N is length of X. There's a length, of course, the function, sorry, I don't remember that. Times N to the power of minus 150. So that's the H. That's 0.9. Sorry? Oh. 0.5-ish. Okay. Now use the standard deviation from this line. So here Silverman actually has one of the rules is that this is equal to 1.06 plus